Our next speaker is Megan Cala. So Megan recently, unfortunately, left the RDCA-DAP team, but she really did tons of work when she was part of the team. She was a scientific director within RDCA-DAP. Today, she's going to present some work she did as part of the Friedreich Ataxia effort. That is a work group under the RDCA-DAP umbrella, and she's also going to show a little preview of new work that is happening, leveraging the continuous, the database that we have in continuous expansion. And she also worked on other things that her intern is going to show to you later today. So welcome virtually, Megan.
Hello, everyone. My name is Megan Cala-Pane, and I'm the Quantitative Scientific Director for RDCA-DAP. During this session, I'll be discussing a case study on disease progression modeling in Friedreich's ataxia. I wanted to start by first defining disease progression modeling and describing the three main classes that fall under the umbrella of disease progression models. This kind of modeling uses mathematical functions to quantify and describe disease changes over time. As I mentioned, there are three main classes that range from purely data-driven or empirical models to fully mechanistic, when the mathematical descriptions from the models can be informed by underlying physiology. And in that case, the disease mechanism information is also available. Regardless of the specific class, all of these models explain trends in longitudinal data with individual patient-level data. At a very high level, this schematic shows an outline or a roadmap of the key steps in the development of a disease progression model, where the end goal here is to have a tool that can be used to inform future clinical trials to be used to generate insights from data. So first is the identification of the mathematical functions that describe the trajectories of the endpoints or biomarkers of interest in the disease. And then we examine the available variables in our data set that could be used to explain the variability in the population with respect to the severity and the rate of progression. Variables can be genetic information or patient demographics, as well as other endpoints or outcome measures. We can also account for additional design aspects like patient dropout effect and placebo effect if we can confirm that the data will support these additional model components. And then we can simulate a symptomatic drug effect and use the model to estimate the sample size that would be required to detect a significant effect. And in a scenario where we have several contending models, we could also use that sample size as a quantitative metric to compare competing models or endpoints. So to put some of this into context, I'm going to relate it to a case study in Friedreich's ataxia, which is a rare genetic neurodegenerative disease. The Friedreich's ataxia integrated clinical database is hosted on RDCA-DAP, and to give you an overview of the FAICD, it contains de-identified patient-level data from the placebo arms of 6 clinical trials and 1 long-term natural history study. So together, this represents just over 1,300 subjects and close to 5,500 observations. And to get a sense of the longitudinal availability, the figure on the left shows each of the studies in the FAICD. That includes both the clinical trials and the natural history study, and the number of subjects or observations at the specified follow-up times throughout the study duration. And then one of the outcome measures included in the FAICD that's used to track FA progression is the Modified Friedreich's Ataxia Rating Scale, or mFARS. And this is displayed in the figure to the right, where individual patient trajectories are represented by the connected black dots, And the red dashed line shows the general trajectory of progression for the whole FAICD cohort. And when we talk about sources of variability within this population, we can consider variability at baseline, which is when a patient would enter a trial and can be anywhere. This can be anywhere along the disease severity spectrum, and it can also depend on trial inclusion criteria. So this figure summarizes the variability within mFARS at baseline. And because mFARS has multiple domains, we can break it down to the individual items of the score, as shown here, to look more closely at the distributions of the item level scores. So the 18 items of mFARS are the bars along the x-axis, and they are grouped into their corresponding domains, which are A, B, C, and E. And the y-axis here is scaled from 0 to 1. So this is the proportion of the individuals in the data set. And then within each bar, subjects with scores available, they were binned based on their severity from min to max, or light to dark orange, which is shown by the color gradient in the legend to the right. And the gray dashed areas also show the scores that are missing from this cohort. And so when you're looking at this figure as a whole, you can see subjects are scoring higher or they're more severe in domain E than, say, domain A. And you can also see individual items where subjects have reached the maximum on the scale at baseline. So in particular, this is observed in several items of those in domain E. So the previous slide showed the variability in the population at baseline, and we can also observe variability longitudinally or with respect to the rate of progression. So still looking at mFARS here, but this time looking at the total composite score. And in Friedreich's ataxia, the progression rate is correlated with individual age of onset, and this can be visualized in the scatter plot of mFARS scores versus age by stratifying or grouping these individuals by their age of onset of clinical presentation. And in doing so, different subgroups can be categorized to identify that later age of onset groups have a milder and more linear increase over all of the observed age ranges. And in general, a faster rate of progression in mFARS correlates with earlier age of onset. So in the case of Friedreich's ataxia, the age of onset could be incorporated into a model of disease progression to quantify some of the variability that is observed in the population. And the math behind these models can be thought of as the backbone and what enables simulations to be run from these models in order to test different scenarios and to answer clinical trial design questions. So I'm not going to go into detail on these different types of base models or the specifics of these equations, but here are some examples that were chosen for the models in Friedreich's ataxia. And when we test these models, we can use various metrics, such as the objective function values and AIC. And these metrics quantify how suitable these various models are in being able to describe and capture the trend of the population. And then after selecting the mathematical structure for the model, the individual specific factors can be probed within the dataset to identify sources of variability within the population. And as I alluded to during the age of onset discussion with mFARS, we can incorporate these various features that present with observable relationships. So this slide shows a particular method that stratifies the population by those various features that are available in the data set. And what we look for are features that deviate from the horizontal line at y=0. So for instance, in this case, the two features that are highlighted with the red dashed boxes would be good candidates to explore because the data shows a deviation from that y=0 line. And this step here is iterative, so it would be repeated throughout the model development process to ensure that the model is well described. So putting all these steps together that I've discussed so far, here are the details of our preliminary disease progression model of mFARS dynamics. And we tested several linear and nonlinear structural models and used a stepwise covariate search to identify that baseline age was a significant covariate on progression, and the functional disability staging score was a significant covariate on baseline severity. So the corresponding parameter estimates, these are summarized in the tables to the left. And then from something called a visual predictive check, that shows that the model predicted mFARS dynamics in the figure to the right. We observed that the model-based confidence intervals, or the shaded bands, do capture the corresponding percentiles from the data. So as a preliminary conclusion, we do believe that we have the structural framework in place for continued model expansion here. And then next, I want to briefly pivot away from Friedreich's ataxia and transition into progressive supranuclear palsy to share how we have been applying some shared learnings to advance model development in this space. So PSP is another rare neurodegenerative disease that causes progressive impairment of balance and walking. And in PSP, a commonly reported outcome measure in contemporary trials is the PSP rating scale, or PSPRS. And like the mFARS in FA, the PSPRS is a multi-domain outcome measure. And specifically, it includes 6 domains as described in the table on the left. And with the data available on RDCA-DAP in PSP, which includes both natural history and clinical trial data, we can observe the trajectories of these 6 individual domain scores from the patient cohort. And this is seen in the figure on the right. And in PSP, we can apply the same modeling methodology that I discussed being used in FA to begin to develop a disease progression model in PSP. So as we observed in FA, the PSPRS is the total composite score, is shown in the figure on the right. As we saw in FA, this is also nonlinear. So we can explore various mathematical descriptions to describe the PSPRS dynamics and its trajectory, as well as incorporate predictors of baseline severity, as well as the rate of progression that can account for some of the variability that's present in the patient population. So these are the initial steps that we have started to explore to advance the development of a disease progression model in PSP. So during the development of disease progression models in FA and PSP, and really model development in general, it's important to understand the data sources, especially when working with aggregated databases, like what we have on RDCA-DAP for FA and PSP. And these aggregated databases include both observational and clinical trials. So in developing a disease progression model, there are additional features that need to be incorporated in the model in order to not only reduce bias, but also to produce a tool that can more accurately simulate realistic clinical trials. So because the data from clinical trials also includes a potential drug effect for the treatment arms and a placebo response for the control arms, the disease progression model that describes the natural disease progression must be modified to include both a drug effect and a placebo effect in order to generate those more realistic trial simulations. So this slide goes into some more detail on the drug effect model and what that could look like for the treatment arm subjects in a clinical trial. And the example here represents a linear disease progression model and what the typical trends might look like for different types of drug effects. So typically we're dealing with a symptomatic drug effect where you can see the disease severity decreases after dosing, but the progression rate remains the same and the severity returns to the natural progression curve after the drug concentration returns to 0. And there can be a different drug effect models incorporated into clinical trial simulator, and these can allow for more flexibility when designing a trial. And then a placebo response model can be added to quantify the magnitude, onset, and offset rate of the placebo response. And this is relevant for control subjects in a clinical trial. So what this typically looks like is something similar to the red curve in this figure, where you can see the disease status temporarily decreases before returning to the natural history disease progression curve. And in terms of duration, relative to a drug effect, the placebo effect is typically much shorter. So again, this is an additional mathematical component that can be incorporated into the disease progression model to generate more realistic trial simulators. So this slide recaps the model development framework that I've presented here today using a case study in FA and some initial work in PSP. So first, the goal of these models is to describe the disease progression of a population or a patient cohort using one or more available outcome measures that well characterizes the disease. In FA, that was the mFARS, and in PSP, that was the PSP-RS. And then we define the appropriate structural and covariate components of the model. This includes defining the mathematical function that captures the population trajectory, also potentially a placebo effect on control arm subjects, a drug effect on treatment arm subjects, and inclusion of any necessary covariates to describe the inter-individual variability within the population. And then lastly, how can we use these models? We can simulate a symptomatic drug effect to assess the sensitivity of the model or the outcome measure. And from the model simulations, we can also estimate the sample size that will be needed to detect a significant effect. So overall, these models can help us to better understand certain patient subpopulations and maximize the data that we have available to describe the variability within these disease populations. So in summary, what I hope to have covered today in this discussion of disease progression modeling is how they can be used to describe trends in longitudinal individual patient level data. And through the case study example in Friedreich's ataxia, I introduced a specific approach using mixed effects as a means to quantify the uncertainty and variability within the disease progression. And what we really want to emphasize is the potential utility of these models in providing the foundation to support clinical trial design with sample size calculations, determination of trial durations, measurement timing, and any other design or key analysis questions that can be addressed through clinical trial simulators, and ultimately generating insightful and actionable solutions. And finally, looking a bit into the future of quantitative modeling in RDCA-DAP. As the platform continues to grow and more data is shared and ingested, the mathematical modeling can be applied to other disease areas, as long as data permits, to be used as tools to help the rare disease community to better understand natural disease history, which we all know is especially challenging in the rare disease space, given the often low number of affected individuals. And as these tools are developed, the intention is to host them on the platform and provide open access to all users in the RDCA-DAP community. And the long-term goal here is to have these tools readily accessible to inform critical clinical trial design questions for drug development and to ultimately accelerate cures in rare disease. Thank you everyone for your time and attention today.